Okay, cool. So we left off yesterday, guys. I hope that's lined up. Anyway, we left off yesterday talking about what things are thermodynamically favored. So we have our entropy, we have our enthalpy, and the universe likes enthalpy values that are negative, which means energy is given out. Energy is given back to the universe. Okay, so the universe loaned us all the energy when it began, and it wants it back. So the universe likes systems that release heat energy, a negative delta H. Remember, the biggest weird thing in this unit is we are not the system. The thing we're studying is the system. So if the thing we're studying is giving off heat, that is thermodynamically favored. We say it is tending towards spontaneity. In other words, it is spontaneous. Things that are spontaneous, the universe likes. Doesn't mean random, doesn't mean crazy. It just means the things the universe likes, things that are thermodynamically favored. We also learned that entropy is our chaos number, our chaos value, and the universe likes things to become more chaotic. The universe wants things to get more chaotic, so the value that is thermodynamically favored is a positive delta S. Okay? So there's a quick review of what we talked about in the past. Any questions before we talk about free energy? So we're going to wrap up enthalpy and entropy and temperature, and we're going to squish them together into one value that tells us whether or not the reaction can give us useful work. And that is, of course, Gibbs free energy. Gibbs free energy is given the formula delta G equals delta H minus T delta S. So Gibbs free energy in kilojoules per mole, enthalpy value, the temperature in Kelvin, and the entropy value. I'll let you scribble that down before we talk about some important points. Yay, something named after an American. Woohoo! Okay. So, a positive delta G means the system requires energy to continue. It is non-spontaneous. A negative delta G means the system is spontaneous and will release useful work. So, a non-spontaneous reactant-favored system would have a positive delta G. This is non-spontaneous. Spontaneous. Non-spontaneous. And a negative delta G is a system that can release useful energy for work, and this is spontaneous. Now, one thing I did mention, I'm going to mention it again, I'm going to mention it again, I'm going to mention it again, is because entropy spills into physics, chemistry is just an arm of physics. It's the dirty part of physics. So chemistry is the dirty part of physics, where you get to do crazy stuff. But because entropy spills into physics, the term for entropy is joules per mole Kelvin. Joule is a standard unit. A kilojoule is not a standard unit. So the value for entropy is joules, so you must divide by what to get the kilojoules? Got to divide by 1,000. So you're going to take your entropy value and you're going to divide by 1,000 when you put it into Gibbs' law, and that's going to allow you to work with entropy and enthalpy together. Okay. Give me a thumbs up if you're ready to move on. Okay, this table is really important. What I've written up here is the Gibbs free energy equation. Delta G equals delta H minus T delta S. Now, temperature is in Kelvin. Can Kelvin ever be negative? No. So temperature term is always going to be positive. Enthalpy. What is the sign of spontaneous enthalpy? What is the sign that the universe likes for enthalpy? Negative. Yeah. The universe likes systems that give out energy. Okay? The universe likes systems that give out energy, that release energy. Some of you are still scribbling the table, so I'll give you a second. We got to fix that. We got to fix the ceiling too. Fix the ceiling after the lecture. Yeah, it's a nice ceiling that vibrates. Acts like a giant guitar string up there. All right, so enthalpies that are negative are thermodynamically favored. What is the sign of thermodynamically favored entropy? Positive. So this is thermodynamically favored enthalpy. This is thermodynamically favored entropy. Using the equation, if you have a negative minus a positive, what is your value always going to be no matter what? Negative. Negative minus a positive will always have to be negative. And this is always spontaneous. So in other words, if your enthalpy is spontaneous and your entropy is spontaneous, your Gibbs free energy will always be spontaneous because they're working together. Give me a thumbs up if that makes sense to you. Good enough. Next, what value of enthalpy is non-spontaneous? Positive. The universe doesn't want to give us any more energy back. Okay? The universe doesn't want to put energy into a system. And what sign of entropy is non-spontaneous? Negative. The universe does not want systems to become less disordered. The universe likes chaos. It doesn't want less disorder. So if you have a positive, remember a positive times a negative is negative? If you have a positive minus a negative, what's it going to be? Sorry, minus a negative. It will always be, did I say that right? Positive minus a negative? Okay, good. So yeah, so it's going to be positive. This is never spontaneous. If your enthalpy isn't spontaneous and your entropy isn't spontaneous, your delta G can't be spontaneous because they're both working together to be non-spontaneous. Okay? Give me a thumbs up. So some of you know where we're going now. If your enthalpy is spontaneous, but your entropy is non-spontaneous, what happens? It's sometimes spontaneous. They fight. Yeah. If your enthalpy is spontaneous, but your entropy is non-spontaneous, the two fight. Ding, ding. And which one determines who wins? What determines who wins? The size of the delta H or the T delta S term. So if your enthalpy says, I'm spontaneous, but your entropy says, I'm non-spontaneous, which one determines, or what determines who wins? Thank goodness. Okay. There we go. There we are. Okay, so thank you. If your enthalpy is spontaneous and your entropy is non-spontaneous, what determines who wins? What's the value of what? Delta H and T delta S. What have we not talked about so far? Temperature. Remember, temperature, we found out yesterday, is the entropy multiplier. Okay? It's T delta S. A large temperature produces a large entropy. A small temperature produces a small entropy. Temperature is the entropy multiplier. So, it is your temperature that will determine if it's spontaneous. So this is going to be depends upon temp. So if one is spontaneous and the other is non-spontaneous, going to be delta H minus T delta S. Or it's going to be delta H minus T delta S. Temperature is going to determine how big the T delta S term is going to be. If you have a very high temperature, you're going to have a very high T delta S term, and entropy wins. If you have a very small temperature, you're going to have a very small T delta S term, and enthalpy will win. Kind of a weird concept. Give me a thumbs up if it's starting to float around your brain. Okay, some of you, about 2/3 of you are getting it. Okay, next. Let's take a look where enthalpy is non-spontaneous and entropy is spontaneous. What happens here? Yep, once again, depends upon temperature. If your enthalpy term is non-spontaneous, but your entropy term is spontaneous, once again, it depends upon temperature. Temperature is the entropy multiplier. Temperature determines whether or not the T delta S term is bigger or smaller than the delta H term. All right. Give me a thumbs up if you understand this and ready to move on. Any questions? Then we're moving on. This is primarily a summary. Negative Gibbs free energy is spontaneous, also called product favored. Positive Gibbs energy is non-spontaneous, which is reactant favored. A delta G of 0 is kind of interesting. It means two things. A delta G of 0 means the system is at equilibrium. Remember equilibrium? Where it's going that way and that way at the same time? Okay, so a delta G of 0 means the system is at equilibrium. But it also means this. The delta G of 0 is the point at which a spontaneous system becomes non-spontaneous. Or a non-spontaneous system becomes spontaneous. No, that would be equilibrium. But it's, you know how like when you do your math, it's just the point at which one side starts to win. Or the point at which one side that was losing is now winning.
So it's like when Frodo puts the rings in the volcano.
Right, it's when Frodo puts the ring in the volcano. Whatever. It's the point at which it's the point at which the enthalpy term starts to win or the enthalpy term starts to lose. And that'll make sense in the exercise we're about to do. Okay. Questions? All right, moving on. So again, this is just another summary. This one's out of your textbook. It's a summary of everything we've learned so far in thermodynamics. So enthalpy, negative is exothermic, positive is endothermic. Entropy, positive is disordering, negative is ordering. Positive delta G is non-spontaneous, negative delta G is spontaneous. And once again, the reason I put it up here is to remind us, when you take your entropy value, you're going to divide your entropy value by 1,000 because entropy is going to be given to you in joules. If you want entropy to interact with enthalpy, it needs to be in kilojoules. Is the phone a distraction? I can hold on to it if it's too much of a distraction. Okay. Give me a thumbs up if you're ready to do practice. Your calculator? Your calculator's warmed up? All right. Okay. Here we go. Very typical exercise. If enthalpy is non-spontaneous but entropy is spontaneous, what determines whether or not the reaction is spontaneous? Temperature. Good. So, moving on. If a reaction has a delta H of positive 340 kilojoules, non-spontaneous, and a delta S of 3240 joules per Kelvin, spontaneous, is the reaction spontaneous at 470 Kelvin? Write your Gibbs law, plug the numbers in, and Is the reaction going to give you a negative delta G or a positive delta G? Do that now. Actually, in this case, size does matter. Yeah. In this particular situation, size does matter because if your delta H is bigger than your T delta S, then delta H wins. So, the universe is going to choose whichever one is bigger. Yeah, so as was chatted about, your enthalpy term is non-spontaneous. Your entropy term is spontaneous. And your temperature determines which one wins. Guys, it isn't a competition. Besides, it's the 21st century. You can have a robot. What number did you plug in for entropy? Very nice, yes. You plugged in 3.240. So positive 340 for enthalpy, 470 for temperature, 3.2, positive 3.2 for entropy. If you got a number, give me a thumbs up. Looks like about 3/4 of you do. Okay, I'll give you 30 more seconds for the other quarter to finish up their calculations. Okay, if you got, ladies and gentlemen, if you got a spontaneous negative delta G, put your hand up. Good. If you got a number that is more negative than negative 300, keep your hand up. More negative than negative 600? More negative than negative 900? More negative than negative 1200? Good. What'd you get? (1182 kilojoules per mole. So the reaction is spontaneous at 470 Kelvin. Okay, make sense? So what did we do? We took a non-spontaneous enthalpy and a spontaneous entropy. Temperature is the entropy multiplier, and because temperature was so high, entropy won, and the system became spontaneous. Give me a thumbs up if you understand what just happened. Uh-oh. Any questions? All right, you got it. Okay, good. Waiting. Okay, backing up. 1, then 2. Okay. You mean the table? It wouldn't hurt, but I mean that's ultimately what we're talking about. Is we have a delta H that is positive and a delta S that is positive. So the two fight, and temperature determines which one wins. We did use the equation. We plugged the numbers into the equation. So we have to plug the numbers in to find out ultimately what the delta G is. For instance, if your temperature was 10 Kelvin, then your entropy term would not be big enough to win, and enthalpy would have won instead. And it would have been non-spontaneous. If your temperature was so small that your T delta S term was really small, then the delta H would have won, and the answer would have been non-spontaneous. the delta G will always be spontaneous when both the enthalpy and entropy term are both spontaneous. So if enthalpy is spontaneous, entropy is spontaneous, delta G is always spontaneous. On the other hand, if enthalpy is non-spontaneous and entropy is non-spontaneous, then delta G will never be spontaneous. There is no temperature that will make delta G spontaneous if they're both non-spontaneous. For delta G. Yes. So for delta H and delta G, negative is spontaneous, and for delta S, positive is spontaneous. Yes, that's why we took it bit by bit. For delta H, positive is non-spontaneous, negative is non-spontaneous for delta S, and positive is non-spontaneous for delta G. All right, next. Next one. If a reaction has a delta H of negative 810, hey, that's spontaneous. And a delta S of negative 1500, that's non-spontaneous. At what temperature is the, or what temperatures, plural, is the reaction spontaneous? So you've got a non-spontaneous entropy, and you've got a spontaneous enthalpy. What temperatures make the reaction spontaneous? What do I do? Yes. What do I do here? Plug in the values. No, you're solving for temperature. But what are you setting delta G at? Everybody go like this. 0. Yeah. Because remember, the point at which something becomes spontaneous from non-spontaneous is 0. The point at which something becomes negative to positive, 0. So set delta G equal to 0 and solve for T. It sounds like from the chatter that you got an answer. Okay, give me a thumbs up if you have an answer. Sounds good. If you got a number that is larger than 100 Kelvin, raise your hand. Larger than 200 Kelvin. Larger than 300 Kelvin. Larger than 400 Kelvin. Larger than 500 Kelvin. Larger than 600 Kelvin. Good, what'd you get? 531 Kelvin. Okay. Did I answer the question? Nope. I've almost answered the question. The question is, guys, the question is, at what temperatures is it spontaneous? So I'm going to need a larger than or a smaller than symbol. So the delta H is spontaneous. The delta S is non-spontaneous, and the breaking point is 531 Kelvin. Do I need temperatures below 531 or above 531? Why don't you think about this? Take a minute or two, think about it, and then tell your friends. And we'll vote here in a second.